So let's also talk about assumptions of rotation-based multivariate techniques. To some degree, that applies to our ordinations that we did with principal component analysis, factor analysis, or canonical discriminant analysis. But where that matters the most is in the application of multivariate analysis of variance, which is just one version or one aspect of discriminant analysis. But here we actually calculate p-values and we make inferences. And rather than talking about this purely theoretically, I do want to illustrate this with some examples. So if we talk about assumptions for all rotation-based multivariate techniques, you may ask, what's the big deal here? What's the assumption of looking at a data set from a different angle? And you would be right, there really is none. So if your data is weirdly distributed, that technically is not a problem. So none of your inferences are necessarily wrong, but they may be slightly misleading or not as enlightening as they could be. And it's kind of the same deal as with non-normally distributed data and summary statistics such as the mean. If you have a highly skewed data set, your mean is not necessarily representative of central tendency. And so we have the same issue here with rotation-based techniques like principal component analysis. So we don't necessarily like skewed distributions, and we don't necessarily want outliers in our data set. And I can just give you a sense of how that affects your ordinations. It's not necessarily an assumption, but it's a consideration. So let's go back to our previous example. I'm just importing the US arrests data here, and I'm going to run the principal component analysis and do a biplot. And you are probably familiar with this by now. We have two major dimensions here at right angles. We talked about this before, so that's nice. But let's assume we have now a crazy outlier in here, something that does not fit with this type of data. And an outlier doesn't necessarily need to be an error. It can be an error, but it can also be something that's just very different. So let's say we add a different country here. And so I have another data set here with an outlier that is Saudi Arabia. So I just came up with some fictitious statistics for murder, assault, and rape, as well as urban population and income for a completely different circumstance. So we could assume that income in Saudi Arabia may be quite high because of all that oil revenue. And because they are, under pretty harsh Sharia law, your general crime statistics may be quite low. But since it also requires 3 independent witnesses to convict somebody of rape, those statistics may be extremely low. So I just put that in. So this is a very different situation, a different justice system, different income levels. So that is likely going to show up as an outlier. So if I have something like this, let's see how that looks. So if I import that data set with that additional outlier, everything else stays the same. And we look at our biplot. So we have Saudi Arabia here now as an outlier. And you can see what that does to my principal component analysis, right? Because there is so much variance between my outlier and all the other states, that drives my first principal component. So it's an irresistible attraction for the first component to cover all that variance between the outlier and the rest of it. So as a result of that, all my relationships that were interesting and insightful also now get messed up. So this is not necessarily wrong. So this is all correct, but it is strongly influenced by that outlier. So if you don't want that, you know what to do. So take this out of your initial analysis, do your principal component without the outlier, and then if you do want to have that in there for reference, you can always bring it back in, and it would come back in a position that makes sense in the original coordinate system. But if you have outliers, they will drive your rotation. So just keep that in mind. So effects of skewed distributions are actually quite similar. So that's similar to this situation. So if I have variables with long tails toward high values or toward low values, those will again drive my first principal component. And we actually did have an example where this was the case. And if you recall, our other example was with the Alberta climate data set. And if we take a look at this, so we had all these climate variables here for different ecosystems. So if we run a principal component analysis on this and we do our principal component plot, you'll see this wide distribution here that really thins out. So that is indicative of non-normally distributed climate variables. And if I had to guess which ones they are, it's the ones that point in those directions. So mean summer precipitation, mean annual precipitation, precipitation as snow, similar number of frost-free days, frost-free period, and so on. So it does drive my first component just because I have these very high and very low values here. And we can just look at a histogram of some of these variables and see how they actually look. And so if I do this, I see, oh, this is highly skewed. So this is precipitation as snow. So in some places I just get a lot of snow, which is in the mountains. Frost-free period, similarly. So I do have a tail toward the other end here. So with very short frost-free periods, and again, those are my mountain ecosystems that have very short frost-free periods. So if I don't want those tails to drive my ordination necessarily, what I can do is transform this data. And so I'll show you how this works in practice, but let's talk about transformations first on the whiteboard. So the idea of data transformations is, if x is your original variable, that you transform the axis where the really big values get reined in a lot and the small values are not as much affected by your data transformation. And the typical options that you have are square root transformations. You can take the logarithm or the inverse. So those are increasing in strength. So inverse is stronger than logarithm is stronger than square root. And so the implementation is really straightforward. You just take the square root of your x data. I put a c here, so always consider putting a constant before you take the logarithm or the inverse or the square root. All your values should always be larger than 1. So if you have negative measurement values or values between 0 and 1, add a constant to your variable first before you do the transformations. So either they don't work otherwise or they behave unexpectedly. And in case of the inverse, what it does is, so big values are going in the denominator, so that means very big values become very small values. So this reverses the order. So if you take 1 minus of that, then your rank order is maintained. So the big values are still the big values. So another thing that you can do with the constants is fine-tune your transformation. So if you find that square root is not quite enough, but logarithm is a bit too much, then you can manipulate the strength of the transformations a little bit. So if the red one is the original distribution and you shift a little bit closer to 1 by subtracting a constant, or the other way around, if your original values are shifted away from your minimum value of 1, that weakens or that strengthens the transformation as well. So let's go back to R and see if we can implement this. So we did have a look at the histogram of precipitation as snow, and that's positively skewed, so we might want to apply something like a straight log transformation. And this one here is an example of a negatively skewed distribution, so we have to flip this one. So in order to do those transformations, we also want to put it as close to the 0 value as possible. So I need the minimum of precipitation as snow, so that's 61. And because I'm going to flip this first and then shift it over, I also need the maximum value of FFP. So this will be my minimum value for the transformation there. So let's have a look at our log transform precipitation as snow. So that's how it was before. If we do a log transform, that's after. But we still have a bit of a tail here. So what we could do is add a constant, and the constant can be a maximum value of 60. But let's try 30 first. So we just shift a little closer to the 0 value. So let's start by subtracting maybe half of that. So that's a little bit better, but I still have that long tail. So let's go for the maximum. So if I want all values to be larger than 1, I can only subtract 60. So let's see how that looks. And Well, that's actually pretty close. So I think that does the job. Otherwise, we would have to go to a stronger transformation like an inverse. But I'm quite satisfied with that. And now let's look again at the frost-free period here. So that's a negative skew. Because it's negative, we have to multiply it by -1 and then add the maximum value so that we shift the whole distribution again into the positive range. So 126. And let's see how that looks. So in that case, we actually went a little over the top. So we did flip it, we did transform it, but we still have the tail on the left. So that means our transformation was a little bit too strong. So let's move it away from the 0 even further. So we can maybe make that 150 and see how that looks. And well, that looks not too bad. So I think we can work with those types of transformations. So if I want to implement this is just visualization, and I have now to modify my original data set. So we'll detach it, we'll do a proper transformation of my original variables. So this would be -60, that's what we figured, and this one plus 150. So that gives us those nice symmetrical distributions with no long tails on either side. So we run those, we attach it again, and then I can go back. So now my frost-free period and precipitation as snow, they are not in original units anymore. So they're not in millimeter or days, but they are transformed into these new axes here with a mean of 4. And I can run my principal component analysis again. But I would have to work my way through all the variables here. So check them all for normality. Then you might get a slightly nicer principal component plot. So sometimes it matters, sometimes it doesn't matter all that much. But if you have really long tails, that can make a difference. So that can change your loadings, and generally your ordinations look a little better with your individual observations more evenly distributed. That would usually be considered a better visualization. Good, and last but not least, let's take a look on the effect of distributions on significance testing. So this is where this might matter. So normality within your groups and homogeneity of variances among your groups, those are considered essential assumptions of analysis of variance. And the same is true for multivariate analysis of variance. So if anything, multivariate analysis of variance is actually slightly more sensitive of ignoring the assumptions of normality. But in the bigger picture, it is fairly robust. So if your data is not normally distributed and cannot be easily transformed, it's not necessarily a deal breaker. We can look at this here with a simple example that we pick up later again. So this is a reclamation data set, and we can look at it, or we can actually look at the entire data set here. This is a data set from a reclamation experiment. So it's a site where we're trying to grow a bunch of plant species, and in order to facilitate this, we have different soil amendments. So we have experimental plots where we put peat or some topsoil that has been saved, or a mix of both. And so then we have a species count here as response variable, and we have a multiple response variable, and we are wondering where we have the best species response overall, where we may have the highest diversity or the highest number of species that pop up. So these are simply species counts in my different plots. So these are all repetitions of my experimental plots. And if we look at our distributions, you can already see these are not normal. So species counts often have these zero inflated distributions. Most of the plots are actually 0, and then you have a few where you have lots. So if I look at all my species here, they all look pretty bad in terms of distributions. They are absolutely not normally distributed. So this should be a problem for multivariate analysis. And once you have these zero inflated distributions, there's also not much you can do with transformations. So this is really kind of a showstopper. But let's run a multivariate analysis of variance anyway and see what we get. You'll see in the lab how that works. So we say what my predictor variable is. These are my amendments. So if we look at this, this is just a string of my treatments. And my species frequencies are my response variable. So if we look at that, It's just those numbers here. It's a matrix. And now we can run a multivariate analysis of variance. And we get a nice effect here, 0.002. So those treatments do have a significant effect. I can follow this up with pairwise testing, which amendment is actually the best one. But I clearly massively violated my assumption of normality. So you could ask, how reliable is this p-value? And luckily, there is an alternative non-parametric test that we cover in 2 weeks. I'll explain to you later how it works, but we can just look at it for now. Just run it and you would get a very similar table. And so in this case, instead of the p-value of 0.02, I get a p-value of 0.01. So this is a proper test where we use a Bray-Curtis distance and permutational multivariate analysis of variance that does not have any kind of issues with this type of data. And I do get the same result almost always, just as the normal multivariate analysis of variance. So you don't have to worry about assumptions all that much. But there's also no reason why you shouldn't use a non-parametric technique that we'll cover later. So this one is just as good. In fact, it has some amazing advantages to normal multivariate analysis of variance. So one of the interesting things is that multivariate analysis of variance is actually not working if you have too many dependent variables. So it worked here with 6 species, but if you had 100 species, if you have more species than you have sample plots, then this one will not execute. But the non-parametric test will work beautifully. So that's one of the reasons why I'm not going to get into MANOVA here too much. We'll cover statistical significance testing in a little bit more detail when we get to the distance-based techniques. But if you don't have too many response variables, then the multivariate analysis of variance works just fine. If you can transform your data, why not? Go for it. That never hurts. But you also don't have to get too nervous if your data is not normally distributed. Usually you still get a robust result here that's quite similar to the one that you get from a non-parametric technique. So with that, I'll let you go and try all these things out in Lab 4 on discriminant analysis and multivariate analysis of variance. And I'm not really explaining in this class the univariate version, so the analysis of variance. But if you are interested in this and you want to refresh your memory on how this works and what the assumptions of analysis of variance are, so MANOVA builds on many of these things. I didn't really explain it in too much detail here because it's a multivariate statistics class. But if you lack this background, you can go to this link here. So this will give you a thorough treatment of analysis of variance with a bunch of videos in Unit 7 and 8. And there's also a more expansive coverage of the assumptions. So that is within Unit 8, this particular video. It covers this in a little bit more detail. So if you do the lab here and I'm talking about residual plots and you have no idea what I'm talking about, then go to this section here that will explain it in more detail.